So in the last class, and probably the last few classes actually, we had been discussing the modeling of the excitation system for a synchronous machine or the conventional machine. So we talked about several types of excitation system, like the DC exciter and the AC exciter and the static exciter. And we gave examples of several block diagrams with their associated functions. We described the functions of each of these, of course, in a brief manner. So then we went on to the modeling part, how we started with the separately excited DC exciter. So as I said, simply this is nothing but a separately excited DC generator. So you have the field being excited from a separate DC source with the field and the field resistance REF and the field coil inductance LEF, and the armature is producing the output that would be ultimately fed to the exciter coil. The generator, the actual machine coil. Okay, so this is the exciter coil, and this voltage output EX, which we treated later on as the EFD, that is the field voltage, that would be directly applied across the DC field of the main generator, that is the synchronous generator. So we went through the some derivation for this, and we talked about this exciter load saturation curve. So we started from some open circuit curve, that is the OCC, where we talked about that without loading, the OCC would look like this. So there won't be any armature resistance drop or armature reaction drop. And at the initial part of this nonlinear OCC curve, if I draw the tangent line, then we would get the air gap line. And of course, if we take into account the armature resistance drop as well as the armature reaction drop, the output voltage from the generator would of course be reduced by some margin, and that reduction is of course nonlinear. So the reduced curve is known as the constant resistance load saturation curve, and this slope which is denoted by the air gap line is denoted by RG, represents a constant resistance line. So we talked about the operating point, and the operating point, we intentionally chose such an operating point which lies on the load saturation curve. And this operating point could be obtained if we decomposed this value of current here. Let's say if this is some value, if so let's say if we get this point as our operating point, and let's say this is any arbitrary value of IEF. So if this is the case, then this IEF could be written as some incremental change in IEF from some fixed value or the initial operating point of IEF, or some steady state operating point of IEF. So this IEF, the relation between this IEF0 and this EX0 should lie on this straight line. So probably in the last class, I drew it wrongly. So I showed it probably here, but that's not correct. Okay, so that point should lie on this straight line, because only then that could be captured by this straight line relation. And of course, this could be written simply as EX0 over RG. So this EX is not any arbitrary EX, rather it is EX0 at this point. But of course, from this curve, we can also identify that this EX0 and this EX0 are actually the same. But when we take this EX0, then we can easily relate it with some linear relationship with IEF0, where the slope between these two, okay, EX0 and IEF0, would give me the RG. This is the RG value. And this is the increment from IEF0. So in total, IEF is nothing but IEF0 plus delta IEF. That is the change in IEF. And this delta IEF is basically taking care of or taking account of the nonlinearity present in the curve, whereas the first part doesn't take into account any nonlinearity. So this is the linear part, and this is a purely nonlinear part. Okay, probably in the last class I mentioned that both of them may take into account the nonlinearity, but that's not correct. Okay, because last class I took the point here, but the point should be here, and that should take into account only the linear part of the IEF expression, that is IEF0, this part. Okay, so with that, this is one thing that I required to mention. This was one problem from the last discussion. And if we continue, so this were the derivation associated for this modeling part. Everything was okay. Then ultimately we went through the part unitization of the expression. And ultimately, finally, we found out some expression here where the super bar or the upper bar for each of these symbols means that all of them are in per units. So this is the first order differential equation. And the differentiation is done for the output voltage of the exciter EX. So if we go back to this diagram, EX is the output voltage of the exciter, which is fed directly to the field circuit of the synchronous machine. So this is the dynamics associated with the exciter output, where we can see that if we rearrange this, so later on what we did, we actually rearranged the expression by keeping the dynamic term or the differential term on the left hand side, and this was the associated time constant. EEF, this was the actual input to the excitation system. That would be actually obtained from the voltage regulator. If I look at the big picture, then this input would be actually a controlled input that would be achieved from the output of the voltage regulator. And then there was some linear function with the gain of the excitation block KE multiplied by the variable EX. And then of course there was the nonlinear function. And nonlinear function was represented like this. The output of this nonlinear block was of course denoted by Vx, where Vx is in general represented by this exponential function. So later on what we did, we tried to simplify this block, a big block, 3 blocks into a single block, by considering the fact that we can linearize this nonlinear model by applying some Taylor series expansion and truncation of higher order terms. So ultimately we found 2 symbols like 2 parameters K and T, where K is some form of gain and T is some form of time constant. And then we saw that, well, the whole thing could be represented simply by this single block, where the gain is K and time constant is T. Input to the block is again the output of the voltage regulator, or deviation in the output of the voltage regulator, and output of this block is simply the deviation in the field voltage, delta EFD. Then we talked a little bit about this block diagram, where we introduced the concepts of control and protective circuits and the associated limiter circuits. And we talked about some voltage sensing and the field shorting and some overexcitation limiter. Those were having some stars with some comments. So in the field shorting topic, I said that, well, that could be, okay, so that is only used for AC and static exciters. And whatever I said in the last class, besides that, you can also consider that the field shorting is also used. There are several mechanisms for implementing the field shorting. So as we can see that it is only used for AC and static exciters, where actually rectification is required. Okay, so the rectification is actually implemented with the help of the thyristors or the diodes. So as we know that those devices shouldn't carry the reverse current. Okay, so to prevent those components of these whole block of this excitation system, or in the rectification block, we want to prevent the reverse current flow through the diode or through the, let's say, SCRs. So to prevent that negative current flow through those components in the rectifier block, we can implement the field shorting. There are several mechanisms. If you want to go in detail for field shorting, you can go through the Prabha Kundur book. Okay, you will find there are probably 2 or 3 methods are mentioned there. Okay, so that was actually done up to this point we discussed in the last class. So let's proceed with some new things today. And to start with, we will look into further detail of this block. That is the excitation system stabilizer circuit. Okay, so as we can see that what it takes inputs from the output of the exciter. So this is the output of the exciter. And it provides some, let's say, stabilizing signal because it is a stabilizer circuit. So its job is to basically stabilize the response of the dynamic system or the excitation system once it goes in the dynamic mode. So the signal is being fed back from the exciter output, and then it should provide some signal to the regulator blocks, specifically in the AC regulator block. So how it could be implemented? There are several ways. Before that, let me explain why and when it is actually present. So we talked about 3 different excitation systems. Among those 3, for the DC and AC excitation systems, which are comparatively slower, okay, slower to response in dynamic domain compared to the static excitation system. Okay, so in the DC and AC type excitation system, if we consider all the blocks associated with the exciter and AVR within this single block, then of course there will be some time delay associated with those. Okay, so that means whenever any signal comes or arrives at the input terminal of this exciter and AVR block, it would take some significant time to arrive at the output of this block. So if that is the case, that means if the time delay is significant, and by significant here we mean that this amount of time delay actually deteriorates the dynamic performance or the stability of the exciter itself. Okay, and specifically this issue is much more severe under open circuit condition. Okay, that means when your generator is in open circuit condition or in offline mode of operation. By offline mode, what do we mean? Let's say if you consider a synchronous machine, this is your synchronous machine, and of course it is a 3-phase machine, so you would expect that there would be 3-phase output. Okay, now as we all know that before running a synchronous generating unit, what we need to do, we actually have to satisfy several conditions. That means, in other words, we can say before paralleling a synchronous machine to the already running system. Let's say there is a big system. There is a big system already supplying power. Okay, this is your power station, and you're already supplying power to the loads. So here you have the loads. Now, if the load demand increases, because we are saying that we are trying to bring on some new generation capacity to the system. So if the load demand increases, then what you need to do, and suppose whatever generation capacity you have here, let's say, those are not sufficient to produce or to satisfy the load demand, okay, even with their maximum capacity. So what you need to do, you need to bring some generator online and you need to couple it to the already running units. Let's say you need to couple it here. Okay, so all the 3 phases here, if I now bring them to the single line diagram, so this would be connected here at the same bus. Okay, let's say if you consider a single bus. Okay, so before doing this, what you need to do, you should run this generator. You should start this generator if it was in idle situation, idle condition. So you should run the prime mover. Okay, if it is a conventional system, you should run the steam turbine. You should heat up the boiler. You should burn the fuel. You should produce the steam, and then the prime mover would give you the, let's say, the synchronous speed. Let's say 1500 RPM. So the synchronous speed, when it runs at synchronous speed, it would take some time to reach at the synchronous speed. That means you have to bring the speed of the generator to synchronous speed by running the prime mover, by burning the fuel, heating the boiler, etc., etc. All these things, all those things has to be done. But after that, what you have to do, you have to excite the field coils. Okay, you have to excite the field coils to get the flux out of the field, so that ultimately you get the voltage output here. So throughout all this operation till now, you haven't actually connected your generation output to the bus bar here to supply the load demand. Okay, what you are simply trying to do, you are simply trying to run the machine in synchronous speed, bring the machine into synchronous speed, and then you are also trying to make sure that, well, the line to line voltage here, let's say if you measure it with the voltmeter, let's say if it is 440, that means the voltage available at this bus from this generator should also be around 440 or exactly 440 in magnitude. So you are also making sure that the voltage is 440. You have to check the phase sequence. You have to check the frequency. Of course, the frequency is checked here because it is running at synchronous speed. So there are actually four conditions before you can bring the unit online and connect. Let's say if there is a switch, then you can close the switch. This is known as synchronization or synchronization of a unit. So before synchronization, actually all the things that are done up to this point, okay, before switching this on and closing this line and bringing the power unit, bringing the generator unit to share some loads along with the already running units, what you are doing, you are running the system, you are running the generator in an offline mode. So this is known as the offline operation. So in offline mode of operation, what you have to do, you have to also make sure that this control, you see this is the excitation circuit. Okay, the voltage that is coming here, I have simply drawn a DC voltage source. However, as you know that there is a complex excitation circuit for exciting this field coil of the synchronous machine. So when I say it is under open circuit condition, means actually this. Actually means you haven't yet supplied the output to the bus bar. It is still trying to reach at this terminal voltage at the synchronous speed. Okay. So under open circuit condition, with this significant time delay for this DC and AC excitation system, AC type excitation system, this significant time delay could produce an unstable performance or poor dynamic performance, poor inherent dynamic performance. Other words, you can say unstable performance or unacceptable performance. So to get rid of this, what we need to do, we need to provide some compensation circuit. And this is one way to implement the compensation in feedback path, okay? Or there are other options without implementing this. You could also try to provide some series compensation here, okay? Series means in series with the exciter and AVR. If you don't use series, then you use the feedback path and you give it a negative feedback. So these are the two ways that is being mentioned here. So you either use the series feedback compensation, you use the series compensation, or you use the feedback compensation. And any of these should be designed in such a way that either of these should enhance the dynamic performance of the system. Okay. Any question? No. Okay, so let's continue. But among these two options, like the series option and the feedback options, the one that we are going to choose is the one that is more popular among these two, and that is the feedback one. And this is known as the rate feedback or derivative feedback. Okay. Why it is known as the rate feedback or derivative feedback? Because of the presence of this differentiator block. You can see the S term here. So even you can, if you want, you can simply put it separately. So if you don't put it here within this block, then simply you can put it as a separate block, which is actually a differentiator block. So because of this S, presence of this S in the numerator, this is known as, that means we are actually taking the derivative of whatever signal is actually coming into this block. Okay. So that's why this S. Now, how this is actually obtained, how this expression is obtained, that is the next question. How are we actually writing this compensation block in this form, like S multiplied by some gain KF divided by 1 plus S multiplied by some time constant TF. So let's take that question now. So this is the example of your stabilizing circuit, we say. So excitation system is stabilizing circuit model. So we can see that this is the armature. This is the armature block. This is the field block. And this armature and this field, both of them actually belong to the exciter. So the whole thing is actually exciter. This is the exciter, comprising of a simple field coil and a simple armature block. This is actually the EFD. Ultimately, this would be EFD. Later on, we'll see that this is the EFD. That is the EX. So what we do, we introduce one stabilizing transformer. Remember, we are talking about the feedback mechanism, not the series mechanism. Okay, the feedback mechanism. So what we do, we take this signal, we take a signal from the output of the exciter, that means from here, and we feed it to the primary side of some stabilizing transformer. Okay, now the question is, what is the type of voltage available at the output of this armature? Is it DC or AC? What do you think?
So DC?
It is DC. So, but still we are feeding it to a transformer, remember. So I will come to that point later. So actually this DC, that is EX, is actually fed. You can see that this plus terminal is going to this side, left side of the transformer coil, and the minus side is going to this lower terminal, the right terminal of the transformer primary winding. And then this is magnetic coupling. Then you have the secondary coil where the voltage induced is V2 and voltage applied or voltage available at this primary side is V1. But this is taken from some DC output, not the AC output. Okay, so this V2 is such that the polarity that is induced, the voltage, induced voltage polarity is like this. Okay, so here it is plus and minus, but here it is not like plus and minus, it is minus and plus. How to achieve this? Simply you can test the transformer polarity test, apply the transformer polarity test, and choose a transformer in such a manner that which provides you such kind of output for such kind of input. Okay, I hope you have gone through the transformer polarity test in your undergrad level. So with that information, you can know that whether when this is positive, this should be negative. When this is negative, this should be positive, and so on. If we applied any alternating input here. Okay, so but here we can see clearly that this terminal is plus, so that means some plus voltage is coming here with respect to the other terminal in the primary side. So ultimately you have some V2 with this polarity on the secondary side of the stabilizing transformer. The current taken by the primary side is I1, and the current output in the secondary circuit is I2. Then we have the error being fed to the system, that is the stabilizing transformer. Secondary transformer is also connected to your some error input. Okay, and if you apply now the KVL, okay, so this secondary side is also ultimately connected to an amplifier. Remember, this amplifier is not the part of the exciter. As I said earlier, the exciter is simply this block. This one is a stabilizing circuit, stabilizing transformer. And this one is simply, you can say this is our voltage regulator VR. Okay, simply represented by an amplifier. Okay. So what the voltage regulator would do, regulator means simply a controller. So what it would do, it would take the error input. The error would be processed somewhere else in the system. So let's go back and try to see from where we could get the errors. So you can easily see in this big picture, the error could be, if it is an AC regulator, the error could be available from here. By error, we mean that is the difference between some reference value and some actual value fed back from the output of the generator. So that means if this is our actual V terminal voltage, three-phase terminal voltage, then that would be sensed and it would be passed through the load compensator, and then the output of that would be taken here. And that would be, of course, compared with some reference value. So whenever this output of this block is something different than the reference, that would be treated as some error to this regulator block. Okay, which is represented simply as an amplifier. Okay. So this is the error we are talking about. Or in other words, that could also be, the error could also be taken from here. And that could be, that means the output of the exciter, that is the DC output, could also be treated here through the excitation system stabilizer, and that could also be taken into the AC regulator in the form of an error. So error could be available from different blocks, either power system stabilizer. If you are designing a power system stabilizer, then that could be a source of error. The output of that signal could be treated as an error. Or the terminal voltage, the AC voltage output from the generator itself could be treated as the source of error. That means deviation of that voltage with respect to this could be treated as an error. The exciter output could be also treated, if when it is passed through the exciter stabilizer circuit, that could also be treated as an input to the AC regulator. So the error has to be calculated with respect to some reference, okay, with respect to some reference. If we are talking about DC regulator, then of course that would go to the DC regulator. So the output of exciter has to be passed through the DC regulator and has to be compared with some DC reference point. Okay. If we talk about the AC reference, then the AC voltage has to be taken into consideration. And we talk about the AC error, AC voltage error, not the DC voltage error. So that means whenever there is any deviation, from the terminal voltage, from the reference voltage, Vref and Vt, any deviation between Vref and Vt, if we talk about the AC voltage deviation, if we talk about the AC regulator. So as soon as there is any deviation between Vref and Vt, then you get some V error. But as long as you have V reference equal to Vt, let's say V reference is set at, 1 per unit. Okay. Just for an example. So as long as your Vt, which would be ultimately passed through some sensing device and some compensating device, load compensating device. So let's say after that we get some transformed or some information about Vt, okay, some information about Vt, and that information is transformed into, let's say, something near about 1 per unit. So in a steady state, we make sure that this is 1 per unit and that is equal to V reference. So whenever you have any load change in the generator side, or there is any fault, any deviation from the steady state operating point, this V reference remains constant. It is not going to be changed because it is a set point. However, this Vt is going to be changed. And consequently, you are going to have some error here at this point. Okay. So as soon as you have the V error, that V error would drive this circuit. Let's see how. So if you now close the loop, try to close this loop like this. So what you would get? You would get V error. Let me try out this. It's not working. Okay. So where we are? So this is V error equals to, this is voltage rise, then you have voltage drop, so V2 plus let's say we put the input to the amplifier, we give it a name, let's say V dash. So this is V dash. So then if we are only interested in the input to the amplifier, so that is V dash, and simply that would be V error minus V2. Okay. So that is V error minus V2. Okay, so this is how we are going to get this expression of the input voltage to the amplifier. Now, in general, there are several types of amplifier, as we know. There is voltage amplifier, there is power amplifier, there is current amplifier. And in this case, we are actually amplifying the input voltage error. Okay, so this is nothing but a voltage amplifier. And from the basics of the voltage amplifier, we all know that the impedance, input impedance to the voltage amplifier is kept to a very high value. And based on that information, we can easily assume that this current that is flowing in the secondary side of the stabilizing transformer, because this input impedance to the amplifier, because this is being a voltage amplifier, this input current to this amplifier would be almost negligible, or it can be assumed to be 0. So thus I haven't put any direction for I2, although I have put some direction for I1. So I2 could be easily neglected based on the information that this is a voltage amplifier and the impedance to this amplifier is pretty high, just to get rid of the loading effect. Okay, if you need more information, you can simply go back and check the basics for voltage amplifier impedance information, input impedance as well as the output impedance. So now let's try to go through the operation a little bit more. So that means when there is any deviation between this V reference and VT that is fed back from the generator terminal, we have this V dash equals to some V error minus the V2. Okay. Now the problem is that, as we all know, that the input to this transformer is actually some DC value. Okay. So if you are feeding some DC value to a transformer, what would be the induced voltage in the secondary? We are feeding some input which is DC to the primary of a transformer. What would be the output? Let's say V1 is EX. Okay, V1 is EX. EX is of course a certain non-zero value, because that is being fed to your synchronous machine field circuit. So let's say V1 is, for example, 1.1 per unit, just for an example. So if V1 is constant at this value, let's say at this point V error is also 0. So what would be V2 and what would be V dash? Anyone? How many of you are there? Let me see. Oh, 11. No one interested in trying this question? Is the question clear? The question is, if you are having a fixed output from here, that output is taken to the primary side of a transformer. So I have taken some value, let's say 1.1 per unit. System is in steady state. There is no error. So V reference is actually equals to VT. So V reference is actually equal to VT under this situation. So the question is, what would be V2 and why? Let's say the
V2 is similar as sir, V2 0, sir.
V2 0. There is
this no error, sir. No error. So
yeah, there is no error. So let's say error is 0. Error is 0.
Okay.
I'm talking about V2 because I want to find out how much voltage would be fed to the amplifier input, because then it would amplify there would be some amplified version of the input, and that would be actually fed to the field coil, and that should change the EX, right? If there is any non-zero value here, that would be amplified, isn't it?
Yes, sir.
And amplification here means you would have more current through the field coils. If you have more current through the field coils, that should increase your EX, isn't it?
Yes, sir.
Okay, now the question is, if there is no error, this is the condition, your V reference is exactly same to your V terminal voltage, or your V terminal voltage is at a steady state. So do you want your voltage output to vary? Because actually when you change EFD, when you change EFD, your terminal voltage would be affected. So at a steady state, do you want that? Do you want that VT should be anything other than V reference?
No, sir.
No. So now tell me, what should be V2 for a fixed V1? This is transformer. Come on.
Yes, sir. Transformer. If
This is DC. This is DC, remember. You have a
yes,
transformer.
sir. এই জন্য স্যার ট্রান্সফর্মার স্টেপ কোনো অপারেশন হবে না স্যার এটার জন্য
Okay, so what would be the output?
সিমিলার অ্যাজ ভি প্রাইম
Similar as V prime. But I'm asking what is V prime? You are saying V prime is V2, V2 is V prime. I'm asking what is V2?
স্যার ডিসি ডিসি তো স্যার ট্রান্সফর্মারে কোনো অ্যাকশন নাই
Okay, so what would be the output? If you give 100 volt DC here, let's say 100 volts DC at the input, 100 volts DC, what would be the output?
Same as input, 100 volt.
Same as input. Okay, this is one answer. But of course, that would depend on number of turns. Okay, anyone else? So answer number 1, 100 volts. Anyone else? Should I call by name now? Okay, so let's start. Naushad, are you there?
ওপেন ডিসি করলে তো ট্রান্সফর্মার ওপেন
I want the answer. I don't need the explanation. I want the answer. What is V2? In one line, in one word, not even one line. No one?
0 ভোল্ট স্যার
This is this is 0 volts. So that is the correct answer. For DC,
0 ভোল্ট
this is 0 volts. Okay, so this is 0 volts. So that means as long as you don't have any error here, remember, as long as there is no error here, you don't want to drive your amplifier, right? You don't want to excite your amplifier. You don't want to disturb its operation. So that means as long as V error is 0, you should make sure that V2 is 0. And that is possible here because we are feeding a DC input to the primary of the transformer. Up to this is clear? So your V error is 0. That means V2 is also 0 because there is no change in V1. This is the most important term. There is no change in V1. So it's a DC voltage and there is no change with respect to time. And because of that, V2 is also 0. So V prime, so V2 is 0. So under these circumstances, V2 is 0. V prime is also 0. So the amplifier doesn't do actually anything because its input is 0. So it doesn't amplify anything. So that means if EX was 1.1 per unit, it will remain at 1.1 per unit. Okay. Now let's come to the scenario that what will happen actually when there will be some positive or negative V error, whatever. There will be some V error, non-zero V error. Okay, so let's see. Some problem with my pen. Okay, so I have to do with the mouse. It's difficult. Okay, so now, okay, so what we told is this. Let us shift it here so that we can have some space. So now the next question is, what would happen if V error is some positive value, let's say. So that means you have V reference and VT unequal. Your terminal voltage is now something different than the reference set point. So V reference is not equal to VT. So that means your V error is non-zero. So if V error is non-zero, this will be fed to this point now at this port. So right at this point, okay, whenever this V error is detected, right at this point, still V2 is 0. Okay, still V2 is 0. Remember, still right at this point, V2 is 0. So that would give you some V prime value, which is pretty high, which is actually just equal to the error. Okay, so if say the error is 0.5, for example, or let's say 0.2, your V dash should be 0.2. Okay, with this 0.2 value, this would be input to the amplifier, and depending on the amplifier gain and time constant, it will take, of course, some time to transmit this signal. And of course, depending on the gain of the amplifier, some signal would be produced here. Whatever signal is produced here, that would excite this field coil a little bit differently. Okay, and based on this excitation, let's say we get some delta I field. Okay, some change in field current, right? Some change in field current would be sensed. Because of this change, what would happen? The output voltage that would be available here would be also a little bit updated, right? This deviation in the output is actually sensed. Remember, this will take some time. So this is a slow dynamic process. This change is not simply like a step. This is a slow dynamic process. So this del IF would be the result of this V dash. Then due to this del IF, we have some del EX. And this del EX would actually produce some del IL or del V1. All the same. Once you have this del V1, this means this del V is actually with respect to time. So this is actually dV1 over dt. This is actually dV1 over dt. So now you see that in the primary side, we have some change in voltage. We have some change in voltage with respect to time. So the transformer primary will be excited. And accordingly, there will be some V2, which is not equals to 0. As soon as you have some other value of V2 other than 0, your V dash would be updated, isn't it?
Yes, sir.
So V dash would be reduced, okay? Because V2 was 0, now it would be some positive value, of course. And then V dash would be reduced. That reduced V dash would again drive this amplifier with some different del IF. And that would produce some different del EX. And like this, because it is a negative feedback system, your system would ultimately create again some V dash, which would be 0. So this is how the negative feedback will actually bring down this V dash value to 0, and there will be no more amplification. Is it clear? And ultimately, what is going to happen? You see, EX, when we are changing this EX, we didn't actually concluded that this delta EX will, of course, affect your VT, remember. So that will actually change your terminal voltage output from the generator itself. Okay. So consequently, you will see that V error is also getting minimized. V2 is also getting minimized. Ultimately, that difference would be driven to 0. So that is the target of this stabilization circuit. And again, once it finds that V dash is equals to 0, V error is equals to 0, again, there will be no more V1 and there will be no more V2, and accordingly, there will be no more V dash. Okay. So this is how it will work. This is the complete process. So the stabilizing transformer will only operate during the dynamic period. Okay, during the steady state operation, there is no need of this stabilizing transformer to be active. Similarly, the amplifier will only work whenever there is any error and when there is any dynamics. Other than that, the amplifier should not be used. It should be sitting idle. So now if I want to model it, remember I said that we have to find out this expression, SKF divided by 1 plus STF. So now let's see how it is being done. So that's pretty straightforward. We simply assume that this primary side of the transformer coil has a resistance R1, an inductance L1. Current through the primary side of the transformer, as I mentioned, there is I1. This L1 is actually the self-inductance, whereas the M is the mutual inductance between the primary side and the secondary side. Similarly, R2, L2 are the resistance and inductance, self-inductance of the secondary side of the stabilizing transformer coil. The current flowing through the secondary coil is I2. However, as we said, that could be assumed to be 0, depending on the high impedance value at the input side of the amplifier. So if I apply the KVL now, simply V1 is the applied voltage in the primary side. Then there will be some drop in the resistive part due to the current flow I1. So that is I1 R1. Then there will be due to this L1, there will be some L di1 by dt. This is S, small s is simply the Laplace operator. Okay, this is the Laplace operator, means in time domain it is d by dt. So this is nothing but L1 di1 by dt. Then there is mutual inductance. That means if there is any current flow in the secondary, there will be some voltage induced in the primary. So that is taken care of by this M, that is modeled by M. So this could be read as M di2 by dt. Similarly for V2, that is R2I2 SL2I2 plus SMI1. Now, as we said, I2 is 0. So simply we get rid of all the elements, all the parts of the expression where we have the presence of I2. So we just get rid of those. So V1 is simply R1I1 plus SL1I1, and V2 again is simply SMI1. Now V2 is the output of the stabilizing transformer. V1 is the input of the stabilizing transformer. So if I want to get the output versus input relation, that is the transfer function relation, that is output by input of a certain block. And by block, we mean here the stabilizing transformer. Simply we take SMI1 in the numerator, that is V2, and the expression of V1 is taken in the denominator. And then we try to simplify this expression by taking these notations, that is KF is M by R1 and TF is L1 by R1. So you see that this expression turns into this expression. Okay, so you have SKF divided by, oh, there's a mistake, there should be STF. Okay. So that is the expression we are looking for, and this is the same as this SKF over 1 plus STF. Okay, and the expression for KF and TF are like this, where TF is, you can see clearly that it is a time constant for some RL circuit. So TF is the time constant and KF is a gain. So that is about the excitation or the stabilizer or the modeling of this feedback or the rate feedback or the derivative feedback stabilizing circuit, which works only during the transient condition and whose job is to actually improve the dynamic performance in open circuit condition, okay, whenever the generator is offline. We continue with some of the other blocks related with our system, like the amplifier block. Simply the amplifier block is represented by a gain Ka, gain of the amplifier, and a time constant of the amplifier. So what is the explanation for this? This means that simply if you have Vi, let's say 1 volts, Ka is 5 volts. If you give some step input of 1 volts there like this, so this is 1 volts, this is 0 volts. If you give some step input, then if the step input is applied, let's say at okay, 1 second, let's say at 1 second, 1.0 second, you apply some step in the input, what the amplifier will do, it will provide a 5 volts output, but after this much of time constant. So at this time constant, actually what it would do, it would reach the 66.67% of the 5 volts. Okay, so if you multiply 5 multiplied by 0.6667, whatever comes, so that is meant by the time constant. So this would be the 5 volts output, V naught versus time. And let's say if this is 66.67%, and let's say if TA is, let's say 2 seconds. So that is the explanation of the time constant. So this is 2 seconds. Okay. So that is the actually the modeling explanation for this amplifier. So it would amplify, but of course, after a certain time, it cannot do it. Of course, in a physical system, you can't expect to be the instantaneous change in gain. Okay. You have to allow some time for getting the gain at the output with respect to the input. So this amplifier block is actually the representation of the magnetic type or electronic type. If we go for the older type, older version, that is the rotating amplifier, that is the Amplidyne block, then you can model it like this. The further detail of this could be found in the literature, and we're not interested in that. So let's proceed on with some of the other blocks. So now we try to introduce some of the limiter blocks or limiter symbols associated with our exciter model. So in the excitation system, we will probably come up with some blocks. For example, some blocks we will be getting like the integrator block. There will be some blocks like the single time constant block like this. There will be some blocks like the gating functions. Okay. So now let's see. Okay, there will be some other blocks like the lead lag blocks. So here we are showing some of those blocks with the corresponding limits. There are basically 2 different kinds of limits associated with our modeling. One is the wind-up limit, another one is the anti-wind-up limit. And both of these limits are actually applicable for the single integrator or single time constant or for lead lag time constant. So now let us see how actually they would affect the output, or how they actually will relate the input and the output, and when there will be the effect of the limit. One thing we have to remember, that all these limits are most probably going to be there if we are trying to analyze the large disturbance stability. Okay. For a small disturbance stability, probably we are not going to reach at these limits. Okay. So these limits are mostly associated with the generalized block diagram or the non-linear block diagrams. Okay. For the linear blocks, until and unless your operating point is somewhere here, somewhere very near to the saturation, okay, very near to the limits, only then probably you would see one of the limits, otherwise not. But for nonlinear system model, nonlinear block diagram representation, or the large disturbance simulation, large disturbance stability issue, you have to incorporate these things or these limits. So let's see the equation one by one. So for this block, what is the system equation? It's pretty straightforward. You can see that this is an integrator. So what you can do, you can simply write it like this. So it is V, that is the output, by the input equals to 1 upon S. Where S is simply the d by dt operator. So if you simplify this, simply this would be dV over dt equals to U. Okay, so this is the system equation. This is what we mean by system equation. That means we are trying to solve this block and we are trying to relate the output and input variables. In this manner, we can achieve the system equation. In the same manner, we can achieve this. How the limiting action will be imposed, let's see. Okay, pretty straightforward. It's pretty straightforward. If your V, this variable here, is within the limits, then of course you can say y equals to V. Where is y? Actually, y is here. So y is actually the constrained version of the unconstrained variable V. You see, V is unconstrained. There is no limit on V. That means V can take any value, but y would be only limited within Lx and Ln. Okay, so y is the constrained version or limited version of V. The limit will be imposed when any of the limit is actually hit by V, because V is unconstrained. So that means you can allow any output here. You can allow at the output terminal of the integrator, you can allow any value, high or low, for this V. But because these actually blocks are actually representation of some physical phenomena, let's say some amplifier block or some what should I say, some other physical phenomena that are to be implemented with the help of these blocks. Okay, some amplifier block, or some integrator block, or some actuator or actuation purpose, for some representing some actuation block, we could use these blocks, either integrator or the blocks that are going to come, the single time constant transfer function, or the lead lag blocks. So all these limits are actually associated with the physical constraints that are imposed on the operation of those devices. Okay, one of those could be simply the saturation. Okay, in the saturation of the field coils or field poles, this is another limiter. You can say this is a limiter. But here we are talking about the integrator, and here we say that, well, this Y, that is the ultimate output, is the constrained version of the unconstrained variable V. So V would be, if V goes beyond Lx, the upper limit, then Y has to be limited to Lx. And if V is something less than Ln or exactly equal to Ln, this limit, then Y has to be limited. So V is unconstrained and Y is constrained. So this is the wind up limit. Okay, in the wind up limit, what happens? The Y value, okay, you see, because we are allowing V to go to very high value. Let's say Lx is, for example, 10, and this is Y. So what it does, what this block does, let's see. V is unconstrained. So let's say V reaches 100. At this point, what should be Y? If this is the situation, what should be Y?
10.
Y should be 10. Excellent. Because let's say probably the actuator doesn't allow, or the valve cannot be opened anymore. Okay, the steam valve cannot be opened anymore, or any other thing, any other physical constraint. Or the amplifier cannot provide you any further gain. Otherwise, it would reach its saturation. Okay, the amplifier saturation problem. So now, if Y has to be updated, if Y has to come away from these limits, it would take, of course, a long time, because then V has to come down to some value from 100. V has to come down to some value which is less than 10, isn't it? In this case, to get some value of Y which is different than 10, V should come down to a value which is less than 10, isn't it? Otherwise, Y should be set at 10. Y should be fixed at 10. Okay. However, in the anti-wind up limits, the thing is a little different. You see the positioning of the limits. The positioning of the limits in the wind up case is after this V, okay, or after this block. Whereas for the anti-wind up limits, it is directly imposed on the integrator. And we don't have any intermediate unconstrained version of V here. We simply have U, and you simply have the output Y. So input is U to the block and output is Y from the block. So you don't have any unconstrained version here. That means you are limiting actually the output of the integrator directly. You are not allowing this winding up of your variable. So this increase beyond the limit is known as the winding up or accumulation. So the system equation remains same. Now the limiting action, we have to check actually two things. Okay, if Y is within the limits, then there is no problem. Of course, dy by dt is simply U. But if Y is beyond Lx, then you have to check another additional condition, that whether the change in Y is also positive or not. If both of these conditions are satisfied, then you set this change to 0. What is this change? This change means actually this dy by dt is actually U. So you make actually U 0. You don't allow any input here, or you pretend that there is no U flowing into the system. and you keep the y constant. That means you are not driving the integrator anymore. That means in this case, whenever you have reached the upper limit, as well as you see the change in y, okay, you change in y, the change in y is also positive, or you can say the u is also positive. So y has reached the limit, or it is going beyond the limit, trying to go beyond the limit. At the same time, u is also positive. Then you set u to 0 and y to the upper limit, and vice versa for the lower limit. So in this manner, this is the difference between this wind-up limits and anti-wind-up limits. That means here you are actually not allowing y, because there is no intermediate variable which is going actually beyond limit to a very high value. So the y will only be changed. Y value can only be changed if the input changes its sign. Okay, if the input changes its sign, then y would be coming away or getting away from the limits Lx. So in this manner, you can also try to go through these blocks. So there is wind up limits for single time constant block, and actually the similar kind of explanation is valid for these blocks too. So because it is a single time constant block, what you would do, you try to find out the system equation. Again, the V is some unconstrained version of the output from the single time constant block. U is again the input. Y is the constrained version or the limiting version of the output from the single time constant block. So if you simplify this, V over U, then you write V over U equals to 1 over 1 plus ST. You simplify the expression, then you would find something like this. dV over dt equals to U minus V over T. So for the wind up limits, this is the case. If V is within the limits, then Y is equal to V like before. And the last two lines are also like before, like this case. So if V is greater than equals to Lx, then you set Y equals to Lx. If V is less than Ln, then you set Y equals to Ln, and so on. For the anti-wind-up limits, we introduce a function now, not the differentiation. We introduce a function f as the output, and we try to look at different values of f. So if for the first case, if we try to examine the limiting actions, for the first case, if y is within the limits, then dy by dt is f. That means f is simply the output. That is the dy by dt available. That is f is u minus y over t. But again, if y is greater than equal to Lx, and at the same time there is difference between u and y in such a manner that u is higher than y. Okay, t is always constant, it's the time constant. So f would be 0 only when the input is higher than the output. Okay, so if this condition is satisfied as well as y reaches the limit, then you set actually u equals to y and y is equal to the upper limit. That means ultimately you are setting u equals to Lx. Okay, that would give you y equal to Lx as well as u equals to Lx as well as f equals to 0. You set f equals to 0, and vice versa for the lower limit. We also have a gating function. Gating function actually allows us to choose between several inputs. Okay, if it is a low voltage logic gate, this is simply the logic gate implementation. So if you have two inputs, if you are looking for a low voltage gate implementation, then always the lower value would be passed. So if you compare two inputs, let's say it's a 2-input logic gate, it's a low voltage, low value gate. LV means here low value gate. HV here means the high value gate. So if U is less than V, simply you pass U. So Y is equals to U. If U is greater than V, then you simply pass the lower value V. Okay, and similarly for high value gate, the opposite is true. If U is greater than V, you pass the higher value, which is U. If U is less than V, then you pass the higher value V in the output. This is the gating function. Okay, so now with all these limiting function and gating function, let's continue to a little bit different thing, that is the terminal voltage transducer and load compensator model. I actually discussed a little bit on this. I actually also discussed about this model, okay, of load compensator. So let's say what it does. Again, we have a quick check on this. This is the load compensator block diagram representation with the expression. So what it needs two inputs. One, with the help of the CT, you record the terminal output current from the generator bus, this bus. With the help of PT, you sense the ET or the voltage available here at this bus. So ET and IT are the inputs to the load compensator blocks. And depending on your choice, that means at which point actually you are trying to control the voltage. Are you trying to control the voltage at the terminal or into the system, from the looking from the terminal into the system? That means your RC and XC would be positive. If you are trying to control any voltage which is further away into the power system, okay, that here I talked about the system, it should be generator. Okay, if I look into the generator from this terminal, if I'm interested to control some voltage which is within the generator, okay, some internal voltage to the generator, then RC and XC would be positive because the voltage would be higher. Any voltage here within the generator should be higher than this voltage. If I'm interested in any voltage that is away from this terminal bus and into the power system, then RC and XC would be negative. And accordingly, you can calculate this VC1, which is the output of this load compensator block. And of course, you use a transducer to actually drive the voltage regulator as well as the exciter block. So the output of the voltage transducer, and the voltage transducer is actually modeled by a single time constant without any gain. So that means whatever input is there, it will be simply passed without any amplification after a certain time TR. However, in the modeling of excitation system, this TR has little effect. So, and the value of TR is pretty less. So sometimes it is also ignored, and you can simply say this VC1 is simply the VC. Again, if you're only interested in ET and IT, that means if you're only interested in controlling the terminal voltage of the generator, then in that case, you simply make RC and X equals to 0. So VC1 will again become ET. So ultimately, you get ET equals to VC. Okay. If you neglect the time constant here, and if you are interested in controlling the actual terminal voltage of the generator, not in your interest is not on any other voltage here or here. Your interest is explicitly on specifically on this terminal voltage ET. So in that case, you can simply make RC and X equals to 0. So simply this ET would be transmitted like this at the input of the voltage regulator. So with this model, we are now ready to study the overall excitation system. This is the example of IEEE type DC1 exciter, which was proposed maybe around 2004 or something like that. I think I have already shared a paper with you, but they have an updated version where they have used IEEE type DC probably 1C, something like that, exciter, where you will see there are some changes, little or subtle changes in this block. Most of the blocks are identical. So let's start. This is the overall excitation system. That means now we have the voltage regulator, we have the exciter, we have the stabilizer feedback, and we have the high voltage gate and lead lag time constant blocks. All the things are now combined together. So this is the first summing junction, and in the first summing junction, what is VC? VC, as we said, VC is the output here. So VC could be the output of the transducer if you take some significant value of TR, if you use some non-zero value of RC and XC. But if you neglect RC and XC, if you neglect TR, then VC is simply the terminal voltage. So that VC is coming here. In simple language, this is the voltage that you are trying to control. This is the voltage that you are trying to control. Whether it is through the transducer, whether it is through the load compensator, that is your choice. Okay. But this is the voltage that you are trying to control with the help of your excitation system. This is the feedback signal. V reference is, of course, the reference signal, could be DC or AC. VS is the power system stabilizer output. We will take this topic later on. So for the time being, we'll consider this to be 0. Then this output of the summing junction is fed as at the second summing junction, where you have some input which is coming from the output of the derivative feedback here, that is termed as VF. Okay, if you remember, this was termed as, okay, we didn't denote it here, but this should be VF. So input should be EFD and output should be VF. So let's go there. Yeah, so input is VFD and the output is VF. Then this is a lead lag time compensator block, which actually models some internal delay or internal, you should say internal things which to the exciter, but these are not the major time constants for the exciter. The major time constant I will define later on. So TC and TB are in general considered to be 0. These represent these model some internal dynamics of the DC type exciter, but they are very low in value, very small in value. So simply to pass this signal, what you simply do, you simply take this one and this one, and you take the TC and TB equals to 0, so that you get rid of any differentiation or integration there. So simply you pass the signal on. This is the HV gate, whose job is to simply take the higher value. Okay, so one of the input is the under excitation limiter. Under excitation limiter could be available here in some model, or could be also treated here. These are the alternate points, alternative choice of VUEL. UEL means under excitation limiter. Okay, it is passed to the high voltage gate, so that always the higher value is taken as the output. And then this is your voltage regulator. This is your voltage regulator, which is simply an amplifier. Okay, so the voltage regulator will be excited, will be energized as soon as there is some error here. Unless there is any error, this should provide you nothing. Okay, no change of VR would be there. So as soon as there is some error, there would be some change in VR, and that would be added up at this summing junction. That would be fed to the exciter. This is the exciter. Remember, this is the exciter. So this is the DC exciter, separately excited DC exciter. This is the voltage regulator, which is simply an amplifier with some anti-wind-up limits. And this is the stabilizing feedback. Okay. If you want to simplify this block, what you do, you get rid of some of the blocks. So you keep your exciter block, because exciter block is necessary. So you keep the exciter block. This is the exciter block. You keep the amplifier, and you get rid of those small time constant. That is the lead lag time constant block is vanished. HV gate, if you want, you can keep it. If you say you are actually, our target is to study the small disturbance stability. So slowly we'd be getting rid of the limits as well as the HV gate and LV gate, all those things. Okay, so you will see that the limits are also not there. Okay, we have gotten rid of the limits. So this is IEEE type DC1A without limits and the inherent time constants. By inherent time constant, we mean TC and TB. So we have gotten rid of that. We have gotten rid of limits. We have gotten rid of gating functions. It looks pretty simple compared to the previous one. And now we rewrite this equation of EFD dot. So again, this Vx is represented as AEX and then some exponential function of EFD. And this is the expression that we derived earlier in one of the classes. We derived this. This is the dynamics of EFD, where EFD was actually considered as EX. If you remember, this is nothing but EX dot. So we derived it earlier. So if we take the time constant on the other side, then we are left with this. So this is the dynamics for the field voltage excitation system. VF dot is simply, if you take this as EFD, and the output is VF here. So if you simply write this as output over input is equals to this transfer function block. And then if you simplify, if you replace the expression for EFD dot here, then you will find this is VF dot. Try to get this on your own. Similarly, what is VR dot? VR is the output of the amplifier or output of the voltage regulator. And what is this here? This is actually the output of the summing junction. So you have VREF plus VS. So VREF plus VS minus VC, this minus, and minus VF. So we have 4 signals multiplied by KA. This is the gain. And if you simplify this, ultimately you will see that you will get the dynamic expression for the voltage regulator also, for the VR, voltage regulator output dynamics. This is the stable voltage rate feedback stabilizer voltage dynamic, output voltage dynamics. So you have 3 more state equations. You have 3 additional state equations. So now you will see that your system dynamics should be increased with the incorporation of this. Okay, now before I proceed, let me try to discuss one thing. Okay, so probably your next or coming Friday, it's a holiday. Okay, it's a holiday. So I'm going to miss one class which I actually planned to have earlier. So will you allow me one class before the break of exam? Any day? Even on Friday, I have no problem. I just want to show the simulation for this. I mean, we will implement this exciter block. We have the third order model, and I have few slides left. So I will explain, I will go through these slides a little bit more, and then I will show you the simulation, and then I will be done. So if you allow, then I will take the class. Otherwise, we have to stop here for the mid exam. Now it's your choice.
Okay, sir. Friday, next Friday, or
What is the majority opinion? This is the
sir.
yes, Rihad or Rahid, sorry. Okay, I get your opinion. What about others?
Sir,
So Friday is okay.
Friday is okay.
exam system নিয়ে একটু কথা দরকার স্যার।
Wait, that okay, বাঙালি সবাই বোধহয় বাঙালি। Yes, okay, তাহলে বাংলাতেই বলা যায়। এক্সাম সিস্টেম নিয়ে আমরা ওই দিনই কথা বলবো ইনশাআল্লাহ।
ওকে স্যার।
আমি অলরেডি মিড আর মানে গত বছরের মিড আর ফাইনালের কোশ্চেন শেয়ার করে দিছি আপনাদের ওই গ্রুপে। আশা করি সবাই দেখেছেন অলরেডি। তো ওই
Yes, sir.
টাইপেরই কিছু একটা হবে, প্লাস ওপেন বুক হবে।
ওকে, তাহলে স্যার ফ্রাইডেতে আমরা ক্লাস করি, সমস্যা নাই স্যার।
হ্যাঁ, ফ্রাইডেতে আমরা বসি কিছুক্ষণ, যারা পারেন বসেন, কারণ আমি ওই দিন চেষ্টা করব সিমুলেশন কিছু বাকি আছে ওটা শেষ করে ফেলার, কারণ আমার প্ল্যানে ছিল ওই দিন ক্লাস হবে, তো হঠাৎ এটা তো চাঁদের উপর ডিপেন্ডেন্ট, ছুটিটা শিফট হয়ে শুক্রবার পড়ে গেছে, তো যার কারণে আমার প্ল্যান মোতাবেক আসলে শেষ করতে পারি নাই। তো ফ্রাইডেতে আমরা বসি কিছু সময়ের জন্য, দেখি হয়তো ফুল টাইম নাও লাগতে পারে, আমার কিছু স্লাইড বাকি আছে এখানে, আর ওই সিমুলেশনটা হয়তো আমি দেখাবো, ওইটা দেখালে তারপরে ক্লাস শেষ করে দেব। ওকে, আর ওই দিনই বাকি ডিসকাশন ইনশাআল্লাহ করব। বাট ফ্রাইডে কখন? ফ্রাইডে কি 8টাতে থাকবে নাকি অন্য কোনো টাইমে হবে?
স্যার একটু পিছায় করলে ভালো হয়।
হ্যাঁ, পিছায়
একটু দেরি করে।
কখন বলেন? 3টায়
Okay,
সমস্যা?
জি স্যার, সমস্যা।
Okay.
আচ্ছা, আপাতত 3টায় থাকলেও যদি না আমার কোনো মিটিং টিটিং পড়ে যায়, ঠিক নাই, এখন তো সব অফিস তো অফ, বলা হয়তো দেখা যাবে 3টায় মিটিং দিয়ে বসে আছে। আপাতত 3টায় থাকলেও যদি মিটিং আমি চেঞ্জ করি ক্লাস টাইম, তাহলে আমি নোটিফাই করে দেব গ্রুপে। ওকে,
Okay, sir.
আচ্ছা ঠিক আছে, থ্যাংক ইউ। আচ্ছা, আসসালামু আলাইকুম।
ওয়ালাইকুম আসসালাম।
আসসালামু আলাইকুম স্যার।
ওয়ালাইকুম।
Always awesome.